In today's video, we're going to begin our discussion on functions. So we're going to look at the definition of a function, we're going to look at evaluating functions, we're going to look at properties of functions, and we're also going to look at something called a difference quotient, and that will come up later on in our course, but we want to at least define that at the start. So the first thing is, what is a function? How do we define what a function is? A function is just basically a pairing between two sets, but we have an additional property that has to be satisfied in order for this pairing to actually be a function. So a function is a pairing between two sets where each element of our first set is paired with exactly one element of the second set. We're going to talk more about that in a second. Okay, what does this mean? First thing I want to do is actually give you a quick definition. You've probably heard of this before, of what our two sets are called. So let's say we've got two sets and we have multiple elements that lie in each set. Okay, your first set that you are mapping from is always called the domain. The second set is called the codomain. Okay. And a function just pairs each element of the domain with exactly one element of the codomain. Okay. You may have heard also of the term range, and that's going to come up in our next video. So for right now, we're just concerned about our two sets. We're not worried about exactly what elements we are mapping to, etc. That's going to come up in our next video. But the thing that we need to be aware of right now is for a function, each element of our domain maps to exactly one element of our codomain. So everything in our domain maps to exactly one element of our codomain. We can come across the situation where an element of our domain maps to the same element of the codomain as one of the other elements in the domain. So we can have the situation where two elements from our first set are paired with the same element from our second set. That's totally fine. What we can't have is for some element that we have in our domain, we can't have that it maps to two separate entries in our codomain. So each entry in our domain has to map to exactly one element in our codomain, but you can't have it where one element in your domain maps to two different elements in your codomain, but two elements in the domain can map to the same element in the codomain. So the blue cannot happen. This thing cannot happen where we've got one element mapping to two different ones in that second set. I want to give you some examples of what you may come across when they ask you if something is actually a function. So we're going to go through a couple different examples here. These can be done in different formats. They can be done in terms of pairings, they can be done in terms of a table, and they can also be done in terms of actually giving you a function. And they may ask you, is this a function or not? So our first example that we're going to have is actually in our pairing notation, where we are given these pairs, where the first element comes from our domain, The second element comes from the codomain. And it tells us, for example, that here 1 will map to 2. So 1 in our domain maps to the element 2 in our codomain. Then there's a 2 in our domain, and that maps to 3 in our codomain. And then this is where we come across our issue, is with these 2 here. Okay. If we think about this again in terms of a quick drawing, okay, we're told that the first entries are in our domain. So we know that 1, 2, and 3 lie in our domain. Okay. It's telling us that 2, 3, 5, and 6 are in our codomain. 1 in our domain maps to 2 in our codomain. 2 in our domain maps to 3 in our codomain. And then it tells us that 3 in the domain maps to 5, and it also maps to 6. So I have one element in my domain that maps to 2 different elements in my codomain. Therefore, this does not represent a function. So this is one example of what you might get, where they give you this pairing notation, where they give you where each element of our domain is mapped to in our codomain, and you have to determine from those pairs whether this represents a function or not. Okay. Another quick example in this pairing notation would be this. So this tells us, again, if you give yourself a quick drawing, I have 1, 2, and 3 land in my domain, and I have 2, 4, and 6 in my codomain. 1 maps to 2, 2 maps to 4, 3 maps to 6. Okay. I don't have any element in my domain that maps to 2 separate elements in my codomain. We're totally fine here. This does represent a function. Another type of problem you could get is where they give you these pairings, but this time it's going to be in a table. So they give you each of your entries in your domain, and then each of your entries in your codomain. And it tells you where each entry in your domain is mapped to in your codomain. So 0 is mapped to 5, 1 is mapped to 6, 2 is mapped to 7, etc. Again, we have this issue at the end. We have that the element 4 is mapped to 2 different elements of my codomain. Therefore, this is not a function. If instead I had the situation where I have 2 different elements of my domain mapped to the same element of my codomain, so both 3 and 4 both map to 8, that is fine. Okay. Each element of my domain is mapped to exactly one element of my codomain. This is totally fine. I don't have one element that's mapped to 2 different elements. So we're totally fine here. This is a function. Another type of problem that you could come across is where they actually give you something in terms of x and y, and you have to determine whether y is a function of x. Okay, so another type of problem is deciding whether y is a function of x. Okay, what does this look like? Well, they could give you this equation something like this. And they may say to you, does this represent a function? From what you're used to, you see equations like this, you would probably think, yeah, sure, that's a function. But given our definition, we actually have to do some manipulation here to see if that is true. The goal here is to see if you can make y a function of x. That means that x would be your independent variable, and you are trying to decide if y can be a function of x, meaning y would be the dependent variable dependent on that independent variable x. So what I need to do here, whenever you are given something like this, where they give you this equation and they say, hey, can y be a function of x? You have to rearrange to say that y equals something in terms of x. So let's start with that. Remember, when you take the square root of something, we have to be aware of both the positive and negative square roots. Okay? Because if I was to take this last line here and I square both sides, I still end up with that same value regardless of whether my right side is positive or negative. So I have to be aware that when I square root, I have both the positive and the negative to take into account. What does this tell me? For any given x value, so let's say I were to take x is equal to 1, I have two different y values. If x equals 1, I could have y is equal to positive the square root of 15, and I also have y is equal to negative the square root of 15. So for one given x value, one value in my domain, I end up with two different values in my codomain. That tells me that this original equation that I had up here cannot be considered a function. Y is not a function of x. This thing here is not a function. Because for any given value of x, I have two separate values for y. They can also just give you, instead of giving you something like this where you have to rearrange, etc., they can just give you y in terms of x, something like this. This would be an easier situation. And ask you if y is a function of x here. Okay? Pretty easy to see for each value of x, we're only going to end up with one value of y. Okay, I don't have this positive and negative situation happening. So y is a function of x in this case, because for each value of x, I have one specific value of y. For the last couple examples, I've been saying that y is a function of x. So our dependent variable is a function of our independent variable. X can equal whatever it likes, and then y is going to be a function of that variable. So it's going to depend on whatever value of x that we have. Hence, it's the dependent variable that depends on our independent variable. Okay. That tells me because y is a function of x, we can actually use function notation. So when y is a function of x, we can instead denote it as f of x, a function of x. Okay, so it's just f with x in parentheses. So we have a function of x. So for example, for our last example that we had, for example 5, I could also write this as that. Okay, I have a function of x. So the reason that we like this function notation is because then I can actually evaluate my functions and write it slightly more easily and slightly more clearly when I do this. So for example, if I want to set x is equal to 1 and find out what my dependent variable would equal, I can just say, okay, I have a function where I want to set x equal to 1. So I can call it f of 1, and I can just plug in 1 and give me that answer. So that would be what my dependent variable would equal when my independent variable equaled 1. So it just helps us whenever we're trying to actually define what our independent variable is going to be. When we actually have a value for our for that independent variable, we can just write it like this instead. So that tells us that 1 would be mapped to 4 over 3 by using this particular function f. What we have done here is something called evaluating a function. Okay. What that means is we have evaluated our function at a certain point. We give a value to the function at a particular value in our domain. Okay. So it tells us at a particular point in our domain where it is mapped to into our codomain. I'm going to do a quick example again of this. So let's say that f of x is equal to 4x squared plus 3x minus 2. I want to find f of 0 and we'll do f of 1. So we're going to find out where both 0 and 1 map to. If you plug in x is equal to 0 into our equation here, I'm going to get 0 plus 0 minus 2, so I'm going to get negative 2. And if I plug in x is equal to 1, I get 4 plus 3 minus 2, which equals 5. Okay, so you just plug in that value for x. And that tells me that 0 maps to negative 2 under this function, and 1 maps to 5. Okay. I want to discuss a couple common types of function that you may come across. First thing is a constant function. Okay. The constant function looks like this. Okay. F of x is equal to a. A is just a constant. Okay. So let's say I had f of x is equal to 3. Okay. That would tell me that regardless of what my value of x is, it's always going to be mapped to 3. Okay. So every single element in my domain maps to that exact same element in my codomain. That's totally fine. That still defines a function because each element in my domain is going to exactly one element in the codomain. It just so happens to be the same element. So that is one type of function that you can come across. The other type of function that I want you to be aware of is something called the identity function. And that is where every element of the domain actually maps to itself. Okay. So that would tell you that your domain and codomain will probably have the same entries in it. That's where the range would also come into play here. But the identity function basically means that every element maps to itself. Okay. The last thing that I want to discuss in this video is something called the difference quotient. And like I said at the start, this won't come up for a while, but you will see this a lot in calculus. So I do want to kind of discuss it sporadically throughout this course, but we will talk about it more at the end. I just want you to be aware of what the difference quotient actually is while we're talking about functions. So if we are given a particular function f of x, so we're given some function f of x is equal to something in terms of x, probably, unless you're talking about the constant function. The difference quotient for that function is defined as this particular formula here. H is just a value right now, okay? We're not going to substitute in H is equal to something. H is going to remain as it is. And X is a variable. This looks like a very weird thing right now, like I said, but it's actually going to be used in calculus when you're looking at different things with slopes, etc. So be aware of this, but it will come up again at the end of this course, and it comes up a lot in calculus. Okay. What I want to do right now, because this will help us as we go on, is to actually find the difference quotient for some functions. Okay, so we're going to do some examples of this. So find the difference quotient for f of x is equal to 2x squared plus 5x minus 3. Okay. So remember, our difference quotient is defined as this. So whenever you do this, just work it step by step. First thing I want to look at is f of x plus h. What that means is, if we look at our function here, we've got a function of x. All I'm going to do here is I'm going to replace each x in my function by x plus h. So I'm going to get 2 multiplied by x plus h squared. So where I had the x, I've put x plus h and I'm squaring that, plus 5 times x plus h minus 3. Okay. So that's f of x plus h. Then minus f of x, so that is just f of x as it shows up. Remember to put this in parentheses because we are subtracting it, and I don't want to lose any negatives along the way. And divide that by f of h. So this time, wherever I've got an x, I'm going to put h. So that would give me 2h squared plus 5h minus 3. What you do at this point is try and simplify down as much as possible. That means multiplying out parentheses. So for this first parentheses that I've got here, okay, I've got to multiply this out. That will give me 2 times x squared plus 2xh plus h squared plus 5x plus 5h minus 3 minus 2x squared plus 5x minus 3 divided by 2h squared plus 5h minus 3. Keep multiplying this out. So now I've got to multiply out these parentheses. So that's going to give me 2x squared plus 4xh plus 2h squared plus 5x plus 5h minus 3 minus 2x squared plus 5x minus 3 divided by 2h squared plus 5h minus 3. Okay. At this point, you just have to cancel out anything that you can and simplify as much as possible. So if you were to kind of get rid of these parentheses, remember you are going to have to make sure that you distribute this negative across these terms. So you get 2x squared plus 4xh plus 2h squared plus 5x plus 5h minus 3 minus 2x squared minus 5x plus 3. So you've distributed that negative. And now you can go ahead and simplify the numerator as much as possible. So I've got 2x squared minus 2x squared. Then I've got 5x minus 5x, and I've got negative 3 plus 3. So that leaves me with 4xh plus 2h squared plus 5h over 2h squared plus 5h minus 3. Okay. That's as far as I can go at this point, because I could pull out an h on the top if I wanted to. If you did want to kind of make it slightly more simple, you can do this. It is completely up to you. But we can't cancel it with an h on the denominator because we don't have there's no h that's in that negative 3 term. So we're kind of stuck at that point. But this is a lot of algebraic manipulation. But the main point that I want to make here is what the difference quotient is. Okay, this is the formula for our difference quotient. And as I said, it will become more clear as we go through this course what this is, and particularly in calculus, it will be used a lot. So all I want you to be able to do is to actually find the difference quotient whenever you are given a particular function. Okay. That's all I want to do in this video. In the next video, we are going to look at domain, range, codomain, and look at that for different functions and be able to find what the domain, codomain, and range is given a particular function. Okay, so I will see you in the next video.